Hey guys, welcome to lecture number 19 in Calculus 1. So this will be the fourth lecture in this chapter, and then we will have one more after this, and then we're done with this chapter. So today we will talk about L'Hopital rule, the famous L'Hopital rule. Well, in this lecture you will learn how to find limits of functions using a very simple rule that will involve derivatives of functions. All right, so let's get started. And I would like to dive directly into the subject and tell you exactly what the L'Hopital rule is. All right, so let's get started. All right, so L'Hopital rule. Well, let me tell you a story about this guy. So this L'Hopital guy, in fact, was not a mathematician. In fact, he was a lawyer, I believe. And I think he paid for some conference, for some mathematicians conference at some point. And then Bernoulli named these rules in his honor. So this is how he got the name. So this is the only instance when you will hear of this name. That's why sometimes people call it L'Hopital Bernoulli's rules, but anyway, let's call them like this. And let me dive directly and tell you the statement of the theorem. So theorem, which is due to L'Hopital. So the theorem says the following. So let f and g be two differentiable functions right, with the derivative of g, with g prime is non-negative, right, on an open interval, right, containing the point, let's say, x naught. Well, except possibly at x naught itself, but anyway. Now we suppose that that the limit as x approaches, let me write it like this, that the limit as x approaches x naught of f of x over g of x, so the limit of this ratio, right, let's say, produces an indeterminate form. And let's say the indeterminate form that we will talk about are 0 over 0 or infinity over infinity. If this limit produces one of these two, then we can apply and that the limit as x approaches x naught of f prime of x over g prime of x is L, right? Where L is a finite number, or it can be plus minus infinity. So we'll say that this belongs to R bar, and this guy will be nothing else than just R, and we will also include these two values, positive and negative infinity, right? Then we can say that the limit as x approaches x naught of f of x over g of x will be equal to L. right? So this is what happens. In other words, you can have such something like the limit. If you have an indeterminate of 0 over 0 or infinity over infinity, you can say that the limit as x approaches x naught of f of x over g of x is the same as the limit as x approaches x naught of f prime of x over g prime of x. So you can say that. So this is the L'Hopital rule, very, it's pretty straightforward, and it will be extremely useful in computing limits of functions, as we will see throughout this lecture. All right, let me point out a remark now. The theorem, so this theorem also applies to one-sided limits, to one-sided limits and limits at infinity, as we have seen, and to limits at infinity. Right? So keep that in mind. We have seen limits at infinity. We have seen how to compute them, and so on. Now, I would like to say another thing. So this is one second remark. We cannot, and this is important, we cannot use L'Hopital rule repeatedly So we cannot use it repeatedly until actually, we can, sorry about that. We can use L'Hopital rule repeatedly. So we can, until we get rid of indeterminates. Indeterminate forms. And I'm going to tell you exactly what are the indeterminate forms. So then I'm going to write them like this. So 0 over 0, but then infinity over infinity. And then we can have infinity over negative infinity, still it's indeterminate form, or negative infinity over infinity, or we can have negative infinity over negative infinity, which is basically the same. So the thing that we need to take care of, basically, everything will reduce to these two. 0 over 0 and infinity over infinity. Keep that in mind. So when you have these two here, look at them here, then you can easily apply the L'Hopital rule. All right, and now let's see some examples. So the first example that I have in mind, so examples. And the first one is the very classical limit as x approaches 0 of sine of x over x. Well, I think I told you about this one, that it's a 1, but now we would like to see. So in this case, you have, when you want to apply L'Hopital rule, you have f of x is sine of x, and g of x will be x, right? And by the L'Hopital rule, so let me write it like this first. We have that that the lim as x approaches 0 of well, first of all, let me write it like this: sine of x over x. First of all, the indeterminate that we have here is 0 over 0, because when x is 0, when x approaches 0, sine of 0 is 0, and we have 0 over 0. So we apply, we're going to write here L'Hopital rule, LH. And this would be nothing else than just the limit as x approaches 0 of sine of x prime. So the derivative of sine of x over x prime. And this would be the limit as x approaches 0 of cosine of x over 1, which is cosine of 0 over 1. But cosine of 0 is 1, so the limit is 1, and that's it. You see, finally, now we have a proof for this fact. Well, you can prove it elementary as well without using L'Hopital rule, but anyway, it will be a little bit more complicated because you have to know some kind of inequalities for it so that you can apply the squeeze lemma. But it's much easier. It's pretty straightforward using L'Hopital rule. All right, now let's see a second example. So we will do a bunch of examples throughout this lecture. The second one that I have in mind is, let's see, the limit as x approaches 0 of 1 minus cosine of x over secant of x. Right, in this case, right, so in this case, f of x is 1 minus cosine of x, and g of x is secant of x. So now, what we're going to do is just we're going to plug it in. So, in fact, we would like to do something. I want you to pay attention here. First, we will notice that the limit as x approaches 0 of 1 minus cosine of x over secant of x, because there will be a danger here. So if we plug it in, you will have 1 minus cosine of 0 over secant of 0. But this will be 1 minus 1 over 1. Secant of 0 is 1. So it will be 0 over 1, which is 0. All right. So, and this is not an indeterminate form. Okay, that's great. But now, suppose you accidentally apply L'Hopital rule. So I want to, so suppose that you accidentally apply L'Hopital rule. I'd like to see what happens. So by applying L'Hopital rule, it happens that, well, the lim, so we have that the limit as x approaches 0 of 1 minus cosine of x over secant of x is the limit as x approaches 0 of 1 minus cosine of x prime over secant of x prime. And now this would give us the limit as x approaches 0 of, well, this would be sine of x. And this guy, secant, would be secant of x times tangent of x. And now, if we do some algebra here, so this would be the limit as x approaches 0 of what? Of, let's write it, sine of x over secant of x times sine over cosine of x. And this would be nothing else than the limit as x approaches 0 of cosine of x over secant of x. But now this would be nothing else than just, if we pass the limit, now it's cosine of 0 over secant of 0. This is 1, this is 1, so it's 1. What happened? So in the first case, I got 0, look at it here. And in the second case, I got 1. Which one is it? You see, this is the real danger with the L'Hopital rule, because you'll be tempted to apply L'Hopital rule every time. And I've seen some of you did it well in the exam. Lucky for you, in the exam was you were lucky you could have applied the L'Hopital rule. But what happened in this case? Because I get 2 different answers, and the moral of the story is the following. So let me point out this remark. Remember, let me write with red. Remember to apply L'Hopital rule only when the limit is indeterminate. This is very, very important. When we apply L'Hopital rule, this is not indeterminate here. So it wasn't any 0 over 0 or infinity over infinity. So that's why the first one is correct, not this one. So this is the wrong answer, 1. So we cannot apply L'Hopital rule in this case. I hope this makes sense, right? Okay, now let me give you another example. Let me take a limit now involving infinity. So let's say limit as x approaches infinity of 2x squared plus 3x plus 1, everything over 3x squared plus 5x minus 2. Well, we have a bunch of methods to determine, to find this limit. Well, I think I told you last time in the last lecture that you can factor x squared, right? The highest term on the both top and the bottom, and then you can just force it as a common factor on both, on the numerator and the denominator, and then you can do some computations. Anyway, I'll leave it to you to do that as an exercise. Now I would like to use L'Hopital rule. So in this case, f of x is 2x squared plus 3x plus 1, and g of x is 3x squared plus 5x minus 2. So now by the L'Hopital rule, we have that limit as x approaches infinity of 2x squared plus 3x plus 1, everything over 3x squared plus 5x minus 2. This guy is the lim as x approaches infinity of 2x squared plus 3x plus 1 prime, everything primes, right? The derivative of this guy, everything over 3x squared plus 5x minus 2 prime. Okay, that's great. Now, this will be the lim as x approaches infinity of the derivative on the function on the top is 4x plus 3, right? Everything over 6x plus 5. Okay, that's great. Now we pass to the limit again. Okay, first of all, this was the, okay, here I have L'Hopital rule, and the indeterminate case was infinity over infinity. This is very important. You need to mention this at first, because in this case, when you have, like I said, infinity over infinity or 0 over 0, then you can apply L'Hopital rule. Now let's plug in infinity again. So you have infinity over infinity again. So again, we can apply L'Hopital rule one more time, because why not? The two functions are still differentiable. And this would give us the limit as x approaches infinity of, let's write it, 4x plus 3 prime over 6x plus 5 prime. And this is, in fact, I can write the answer directly. It's 4 over 6, which is 2 over 3, and that's it. Right? Okay, so that was the third example. Now let's see another one. Let me see the following one. So find the limit. This is not as trivial as the others. So this is the limit as x approaches infinity of x times e to the power negative 2x. All right, and I would like you to be very careful here. So let's look. So now let's see what kind of indeterminate form do we have. If you pass to the limit, so we have e to the x approaches infinity, then e to the negative 2x will approach e to the negative infinity, so it will approach 0. So it will be infinity times 0 at first. But now there is a question: can we transform this infinity times 0 to make it look like infinity over infinity or 0 over 0, so that in such way that we're in a good position to apply the L'Hopital rule? That is the question. And yes, we can do it by simple algebraic manipulation. This guy here, if you look at it, can be also expressed as the limit as x approaches infinity of x over e to the power 2x. So pay attention here. So I wrote this as a fraction. And now, if you look at this guy, the indeterminate, so it's infinity over infinity. Wow, that's good. So I can apply L'Hopital rule, and this would be nothing else than just the limit as x approaches infinity of x prime, everything over e to the 2x prime. And this is the limit as x approaches infinity of 1 over, and now let's compute the derivative of this guy, right? And this would be what? This would be 2x prime, right, times e to the 2x. And this is nothing else than just the limit as x approaches infinity of 1 over 2 times e to the 2x. And this guy clearly is 0 because I plug it in infinity and that's it. So this is what happens when x approaches infinity, positive infinity. But here's a question for you. What happens, or maybe I should say directly, what about the limit at negative infinity? X times e to the negative 2x. What about this guy? What do you think? Do you think the limit is still 0? Well, you might be surprised. I'll leave it to you as an exercise, so to show that the limit is not 0. The limit actually will be, anyway, I'll leave it to you. So try to figure it out. So in this, you can do this in the same fashion, but you'll see that something happens here. Anyway, all right. Now let me veer towards saying a few things about other indeterminate forms, because I think I mentioned one of these. You see here, I mentioned this one here, infinity times 0, but I would like to mention others as well, so that you can see that we can apply L'Hopital rule in other cases as well. So other indeterminate forms. Okay, this is important. So other indeterminate forms are the following. We just mentioned them. So there are 1 to infinity, 0 to 0, infinity to the power 0, infinity minus infinity, infinity times 0, right? And of course, the other two that we mentioned, that it's 0 over 0 and infinity over infinity. So these are all indeterminate forms. So you have seen that these two guys, we will deal them with L'Hopital rule. But what about the others? You see, there are a bunch of them. 1, 2, 3, 4, 5, 6, 7. 7 of them. The question now is, we would like to address the following question. Is there a way to convert okay, so these are first 5, right? To convert some of the indeterminate forms in red to 0 over 0 or infinity over infinity? That is the question. So that's the big question that we would like to answer. Well, and of course, once we do this, maybe we can evaluate it. As you have seen, I can apply L'Hopital rule. So that is my my goal. And now let's see some examples. And the first example that I have in mind is the following. It's a pretty famous limit. So it's the limit as x approaches infinity of 1 plus 1 over x, everything to the power x. So I'd like to compute this guy. Well, first, let's see what kind of indeterminate do we have. So the indeterminate form, if we pass to the limit, 1 over x will be 0. So the indeterminate is 1 to infinity. All right, so what can we do? All right, let's do the trick is the following. Well, when you have power to the power, a function to a power another function, then you have seen this when we computed derivatives that maybe we should take the natural log. So this is what's going to happen in this case as well. So let L be the limit as x approaches infinity of 1 plus 1 over x, everything to the power x. Now we're going to take the natural log. So take the log and we have that ln of L is nothing else than just the ln of the limit. So the limit as x approaches infinity to 1 plus 1 over x, everything to the power x. But we know that the limit will commute with the log. So the limit, the log of the limit is the limit of the log. So this would be the limit as x approaches infinity of ln of 1 plus 1 over x, everything to the power x, right? So this will give us, so this is the limit as x approaches infinity of x ln of 1 plus 1 over x. Okay. And now let's see, what kind of indeterminate do we have here? If we take the limit as x approaches infinity, we'll have that this is x. So it's infinity times ln of 1 plus 0. So if infinity times 0. Well, maybe we can transform this into something else. So maybe we can make it look like nicer. So we can write this in the following way. So it's the limit as x approaches infinity of ln of 1 plus 1 over x, everything over 1 over x. Okay, so at this point, this guy here, so the indeterminate here, it's 0 over 0, right? So we can apply L'Hopital rule. So this would be equal to the limit as x approaches infinity of ln of 1 plus 1 over x prime, everything over 1 over x prime. So this is the limit as x approaches infinity. And now this guy will be, so let's write the derivative of this guy. So it will be 1 over 1 plus 1 over x times 1 plus 1 over x prime is negative 1 over x squared. Everything over negative 1 over x squared. Oh my. So this would give us, so let's be careful here, right? So well, there are no mistakes, okay? So this would be, if we do some algebra, so this would be the limit as x approaches infinity of what? Of 1 over 1 plus 1 over x. All right. So this is 1 over 1 plus 0, which is 1. Okay, that's great. So it follows that ln of L is 1. So L is E. So the limit is E. Pretty beautiful, isn't it? So this is what happens when you have power to some power. Basically, you have this indeterminate, 1 to infinity. Then you can definitely apply L'Hopital rule, which is pretty great. Okay. That's great. Now let's see another example. So another example that I have in mind is to find this limit, and let's denote this by L. The limit as x approaches 0 from the right of x to the power sine of x. First of all, what kind of indeterminate form do we have here? If we plug it in, so the indeterminate form is what? Is 0 to the power 0. All right, great. So we cannot apply L'Hopital rule in this case, so maybe we should do something. And again, since we have a function to the power another function, then we can definitely take the log. So we have that ln of L is ln of the limit as x approaches 0 from the right of x to the power sine of x. And this would be, well, the log will commute with the limit, so this would be the lim as x approaches 0 from the right of ln of x to the power sine of x. And this is nothing else than just the limit as x approaches 0 from the right of sine of x times ln of x. All right. Now let's do this again. Sine of 0 is 0. Ln of 0 plus will be infinity, so it's infinity over infinity times 0. Sorry. So maybe we should write this in a certain form so that we can apply L'Hopital rule. So we can write it so that we can have 0 over 0 or infinity over infinity. And yes, we can do it. And we do it in the following way. So this will be the limit as x approaches 0 plus of ln of x. I'm going to keep it like this because I don't want to compute the derivative of 1 over ln of x over 1 over sine of x. Although 1 over sine of x is not pleasant either, but anyway. Okay. Now, the indeterminate here we have, it's infinity over infinity. That's good. So by applying L'Hopital rule, this would be nothing else than just the limit as x approaches 0 from the right of ln of x prime, everything over 1 over sine of x, everything prime. All right, that's great. This would be equal to the limit as x approaches 0 plus of ln of x prime, it will be 1 over x. And this guy here, oh my. So it will be, okay, that's cosecant of x prime, okay. and the derivative of cosecant is negative cosecant of x times cotangent of x. Well, we can actually compute it, but that's fine. You can use the chain rule or the quotient rule. You can do it either way. And this would be the limit as x approaches 0 from the right of, let's see, 1 over x. And now we can write the cotangent and cosecant. So this would be nothing else than just negative cosine of x over sine squared of x. Or if you want, this is nothing else than just the limit as x approaches 0 from the right of negative sine squared of x, everything over x cosine of x, right? All right, and now let's see, what else can we do here? So we can, as you can see, now we're in a good position. Again, we'll have 0 over 0. You can apply L'Hopital rule if you want to, but you can also write it in the following way. The limit as x approaches 0 plus of sine of x over x times negative sine of x over cosine of x. And this is nothing else than just the limit as x approaches 0 from the right of sine of x over x times the limit as x approaches 0 from the right of negative sine of x over cosine of x, right? Which is nothing other than just the tangent. But all right, this one here is, remember, we did it, and so this is 1, and this guy here is 0. It will be 0, and that's it, right? Again, pretty straightforward. Now let's see some other another example, the third one, where we would like to use, and this time we will have an indeterminate, let's say what the indeterminate. So we had 0 to the 0. We have, what else did we have? Okay, maybe infinity to the power 0. So maybe we should compute, so find this limit. So the limit as x approaches infinity of x to the power 1 over x. So the indeterminate form here is infinity to the power 0. Okay. All right. So again, taking the log, ln of L is ln of the limit as x approaches infinity of x to the power 1 over x. And this would give us ln of the limit as x approaches infinity of 1 over x ln of x, and the log commutes with the limit. Okay, just a second. So this would be the limit of the log. Okay, and now this would be equal to the limit as x approaches infinity of ln of x, 1 over x times ln of x. Or if you want, this is the limit as x approaches infinity of ln of x over x. And now, thank God, we're in a good position. So this would be infinity over infinity. So we can apply L'Hopital rule. And this would be the limit as x approaches infinity of ln of x prime, everything over x prime. And this would be equal to the limit as x approaches infinity of 1 over x over 1, which is nothing else than just 0 over 1, which is 0. Are we done? Nope. It's ln of L is 0. So L would be e to the power 0, which is 1. And that's it, right? So this is how you compute using L'Hopital rule, something like this. And now, let me mention one last thing before I go. Special limits involving e to the x and ln of x. I'd like to mention this, and you can actually you can prove this by just doing the L'Hopital rule repeatedly. So we have the following theorem, very important theorem, so which will concern limits involving exponentials and logarithms. All right. If k and n are positive numbers, then we have the following. Let me write them with in red. The limit as x approaches 0 from the right of ln of x over x to the power n is negative infinity, right? Then the limit as x approaches infinity of ln of x over x to the power n will be 0. Then the limit as x approaches infinity of what else we have here? E to the power, let's say, kx over x to the n will be infinity. Right? And the limit as x approaches infinity of x to the n, this is tricky a bit, times e to the negative kx, this will be 0. Okay. So keep this in mind, right? These limits. And you can prove them by just applying repeatedly a L'Hopital rule, right? You can apply L'Hopital rule as many times as you want. You can apply it once, twice, 3 times, and so on. You can keep going until you get there is nothing to do. Okay, guys, I think I'm going to stop here. So this sums up everything for lecture number 19. It was a little bit shorter. The next one will be, again, and the next one will be the last one in this chapter before we start chapter number 5, which will involve integrals. So lecture number 20 will be about optimization in physical sciences, economics, engineering, business, and so on. So it will be, again, a short lecture. Okay, I think it's a good place for me to stop. Thank you very much.